6.5, the central limit theorem. All right, what the central limit theorem says is that for all sample sizes, all samples of the same size n with n greater than 30, this is very important here, n must be greater than 30, the sampling distribution of x bar, or the mean, can be approximated by a normal distribution with mean mu and standard deviation sigma, that's population standard deviation, divided by the square root of n. All right, so what that allows us to do, let me find a good example here. That will allow us to find like the probability of a group of people doing something. Like say that I wanted to know the probability that a group of 50 randomly selected adult men weighed over 200 pounds. So I could figure out a probability like that. So far, we've only been able to figure out a probability of, say, one person or one object. With the central limit theorem, we're able to figure out the probability of, say, like this problem right here, 36 adult females or 49 adult females. Now, if you notice, a lot of your problems, they do 1, and then they do, like this one does, 49. So when you do 1, you work it out just like you did from 6.3. If you work it out with 49 adult females, the only thing that really changes in the problem is that we have to have, for our, I'll show you here, for our formula, instead of just a sigma when you're finding your z-score, it's sigma divided by the square root of n. Again, the big difference is if you're trying to find the probability of a number greater than 1 of something happening, in your z-score, instead of just x minus mu over sigma, the way you find your z-score is going to be x minus mu over sigma over the square root of n. So you have to figure that out. You have to subtract the numerator and then divide by whatever that is. Okay? All right. Practical rules commonly used. For samples of size n larger than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. Alright, so n needs to be greater than 30. Now the only time that we can work problems finding probability when n is not greater than 30, when you know that the original population is normally distributed. So if you know that the original population is normally distributed, it doesn't matter how big the sample is. It could be 10, it could be 2. If you know that the original population is normally distributed, then the number of items in the sample doesn't matter. But if you don't know that, but you have an n larger than 30, you can do this anyway. Okay. Now in your formula, we use the same, really the same mu. This is mu sub x bar. That's the mean of the means, right? It's the same value. This that's in the denominator I showed you is now sigma over the square root of n. Okay. You know that if something is normally distributed, it does kind of have a bell shape to it. Okay, so if you're told it's normally distributed, then it is going to be approximately bell shaped. Uniformly distributed, it would, if it's a uniform distribution, then they're pretty much all the same all the way across, maybe not exactly. This right here says a U-shaped distribution. See this right here? like a U shape here. As the sample size increases, the sampling distribution of sample means approaches a normal distribution. So the larger the sample size, the better the chance that the sampling distribution approaches a normal distribution. So it will be bell-shaped. All right, let's look at this problem. So with the methods that we've known so far, before this section, we wouldn't be able to figure this problem out. All right. So it says, suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming the worst case scenario in which the passengers are all male, what are the chances the elevator is overloaded? And then it tells you assume male weights follow a normal distribution. That's key to this problem. It has to be normal distribution since the n is less than 30. With a mean of 182.9 and a standard deviation of 40.8. All right. Part A wants to know, find the probability that one randomly selected male has a weight greater than 156.25 pounds. All right, so for part A, we're selecting one randomly selected, and we want to know the probability that the weight is greater than 156.25. So our x in part A is 156.25. It's also important that the problem said greater than. We use that whenever we look back at our z-score chart. All right, so we need to find a z-score for this. So x minus mu over sigma. All right. So 156.25 minus 182.9 divided by 40.8. So here's our z-score. Let's round that to two places. Negative 0.65. Now it's important that we understand when we have greater than and we use our table that we're going to have to say 1 minus whatever value we get. Okay, so let's go to our z-score chart. We got a z-score of negative 0.65. So see where the 5's column is. Here's the 5's column, so keep that in mind. And negative 0.65 is 0.2578. So we use 0.2578. But since it said greater than, the probability that the randomly selected person weighs more than 156.25 is 1 minus point, what was it, 25, let's see what the other numbers were, I don't recall, 2578. All right, so minus 0.2578, so 0.7422. So that means that there is a 74.22% chance that if you randomly select an adult male, their weight will be larger than 156.25. Alright. So we should have been able to do that before looking at this. Let's see what Part B gives us. Find the probability that a sample of 16 males have a mean weight greater than 156.25. It says, which puts the total weight at 2,500 pounds, exceeding the maximum capacity. Alright, so 16 is the number of males. So that's our n. So when we say z equals x minus mu sub x bar, which is the same thing as mu, over sigma divided by the square root of n, our n is 16. Alright, so we say 156.25 minus what? What's the mean of men? 182.9 divided by, here's the difference, we still say 40.8, but it's that divided by the square root of 16, or 4. Okay. So what I would do, if you want to use the Windows calculator, you can just put that in parentheses, 156.25 minus 182.9, close parentheses, divided by, then I would open parentheses, 40.8 divided by 4. Now you could put in square root or whatever. I'm going to close the parentheses, so you see I'm subtracting up top and then I'm dividing by something that I'm dividing. So, and that gives me a z-score of negative 2.61. So I need to go, and we want to know greater than. So let's go to our z-score chart. All right, negative 2 is here, 0.61, 0.0045. Now, since we want to know the probability that the average weight of 16 men would be greater than 156.25, that probability that x is greater than 156.25 is equal to 1 minus 0.0045. So that's 0.9955. So that means 99.55% chance that if you randomly select 16 males, their average weight is over 156.25. Pretty good chance. Guess that's why they have those buzzers on the elevators that go off. I've heard that before. You get a lot of people in the elevator, sometimes too many, and you hear a buzzer go off. They'll tell you you're at a too big of a weight. I guess it would depend on the elevator. It'd be kind of discouraging, but somehow I've managed to live after I heard that. So, all right. So that's the central limit theorem. That allows us to find a probability if we have a group of more than just one. If we have a group of, like on this problem, 16. The important thing is that when using the central limit theorem, either you know that your original population is normally distributed, or your group, your sample, is larger than 30. If it doesn't meet one of those two, then you can't use this method. You can't use the central limit theorem. Okay. And so they did, here's a slide. They did the same thing we did. Found the area. That was for 1. And then they found that probability for 16. All right, correction for a finite population. When sampling without replacement, and I don't know that you'll need this formula. I just want to go over it real quick. I don't think your homework or you're tested on this. When sampling without replacement, and the sample size n is greater than 5% of the finite population of size capital N, that is, lowercase n is greater than 0.05 of capital N, adjust the standard deviation of sample means by multiplying it by the finite population correction factor. And this right here, it says this part, this is the finite population correction factor. So that would be, capital N would be like the entire population, lowercase n would be the sample size. So you'd have to do that over capital N minus 1, take the square root of that, and then multiply it by the sigma divided by the square root of n. Like I said though, pretty sure you're not going to have to worry about that so much. Okay, and so that finishes section 6.5. All right.